Chapter 1. The Vine That Changed the World. The history of human civilization is frequently written in the heavy industrial languages of iron, gold, and fossil fuels. Yet, one of the most profound catalysts for global exploration and economic transformation was a small, wrinkled seed born from a climbing vine in the humid jungles of southern India. Long before the first European galleons dared to navigate the treacherous, storm-tossed waters of the Cape of Good Hope, this humble fruit dictated the wealth of maritime empires. It was a botanical commodity so universally desired that it served as an international currency, paid the ransoms of besieged cities to barbarian kings, and built the foundations of the modern global spice trade.
This is the story of Piper nigrum, an aggressive, climbing botanical engine. As a biological organism, it is remarkably uncompromising, demanding a highly specific convergence of atmospheric moisture, dense shade, and weathered soil chemistry to survive and reproduce. When the precise, exacting ecological demands of this jungle vine were met by the unique geography of the Indian subcontinent, it produced a crop that permanently captivated the human palate. The resulting spice was black pepper, a substance that would forever alter the culinary, medicinal, and economic landscape of the human race. To understand the profound global obsession with black pepper, one must first deeply understand the living organism that produces it. The physical earth and the pepper vine are not passive background elements in this historical drama. They are active, dictating characters that force human beings to adapt to their rhythms. The vine demands a towering host to climb, the porous soil demands relentless rainwater to drain, and the delicate fruit demands careful, dangerous extraction from the canopy. Only by mastering this complex, high-altitude ecological web could ancient humans harvest the chemical illusion of fire that lay hidden within the green berries. The botany of Piper nigrum, the plant responsible for the world's most ubiquitous spice, Piper nigrum, is a perennial, evergreen climbing vine belonging to the botanical family Piperaceae. In its natural wild habitat, it behaves as a climbing botanical engine, utterly lacking the rigid woody trunk necessary to support its own vertical growth toward the sun. Instead, it relies on a parasitic-like need for structural support, aggressively seeking out the rough bark of towering jungle trees to carry its foliage upward into the light of the upper canopy. Without a host tree to cling to, the vine would merely snake aimlessly across the dark forest floor, vulnerable to fungal rot and entirely incapable of producing its valuable fruit. To achieve this necessary vertical ascent, the vine utilizes highly specialized adventitious roots, which are short clinging appendages that sprout directly from the nodes of the plant's main stem. These slender thread-like roots reach out blindly to grip the bark of native host trees such as the jackfruit, the mango, or the silver oak. Once physical contact is made with the host, these adventitious roots secrete a naturally adhesive, sticky sap that rapidly dries and hardens upon exposure to the open air. This organic biological cement firmly anchors the vine to its host, allowing it to scale sheer vertical heights of up to 30 feet in pursuit of the sun-dappled light it requires for basic photosynthesis. Once the vine has successfully secured its position high within the jungle canopy, it begins to alter its growth pattern, extending lateral, fruiting branches horizontally outward into the open air. And these lateral branches, often referred to as plasiotropes, are the only parts of the entire plant capable of producing the delicate floral spikes necessary for sexual reproduction. Each slender hanging spike can host anywhere between 50 and 150 microscopic yellowish-green flowers arranged in dense, compact clusters. Cultivated Piper nigrum vines are predominantly hermaphroditic, meaning they possess both male and female reproductive organs within the exact same flower, a biological trait that allows them to highly effectively self-pollinate. However, the transition from a dormant climbing vine to an actively flowering organism is entirely dependent on a dramatic and highly specific environmental trigger. The vine operates on a strict, unforgiving meteorological clock, requiring a sudden, massive deluge of water to shock its biological systems into reproductive action. Botanical research indicates that the plant must receive exactly 70 millimeters of rainfall uniformly distributed over 20 days, typically during the humid months of May and June. This precise influx of warm moisture breaks the plant's dry season dormancy, triggering the flushing of new green leaves and the explosive emergence of the flower spikes. Once this delicate biological sequence is set into motion by the rain, the vine enters a highly vulnerable 16-week critical period. From the exact moment of flowering to the final ripening of the fruit, The plant demands continuous, uninterrupted showers to maintain its high cellular water potential. If the rains prematurely cease and a dry spell occurs for even a few consecutive days within this 16-week window, the delicate flowers will rapidly abort, the floral spikes will shed from the branches, and the ultimate crop yield will utterly collapse. The vine's fruiting cycle is therefore entirely at the mercy of the sky, requiring an exact rhythmic sequence of environmental stress followed by prolonged moisture relief. When the climatic conditions are perfectly met, the microscopic flowers undergo fertilization and begin the slow process of fruiting. The fruit that eventually develops on these hanging spikes is a drupe, a fleshy stone fruit similar in basic anatomical structure to a cherry or a peach, albeit microscopic by comparison. Measuring a mere 5 millimeters in diameter, this tiny, spherical green fruit encases a single, incredibly hard seed at its core. It takes a grueling 6 to 8 months for the drupe to reach full biological maturity, slowly changing in skin color from a vibrant bright green to a deep yellowish red as its sugar content increases. Because the vine is so highly sensitive to fluctuations in water availability, it has evolved highly specific internal mechanisms to survive brief periods of drought. During unexpected water deficits, the plant rapidly increases the thickness of its abaxial epidermis, the lower layer of its leaves, to prevent critical water loss through transpiration. Simultaneously, the vine heavily increases its stomatal density, allowing it to highly efficiently regulate the exchange of carbon dioxide and oxygen even when moisture is scarce. Despite these impressive physiological adaptations, prolonged water stress will inevitably force the plant to abandon its reproductive efforts, sacrificing its fruit to ensure the survival of its climbing stems. It is this profound biological sensitivity that kept the cultivation of black pepper restricted to a very specific geographical zone for thousands of years. And the vine is not an adaptable generalist. It is a highly specialized organism that requires an environment capable of delivering massive, predictable volumes of water without simultaneously drowning its delicate root system. It is this tiny, fleshy stone fruit, born of clinging, adhesive roots and relentless tropical rain, that the ancient world would eventually come to value as highly as precious metals. To find the exact environmental conditions capable of sustaining this demanding botanical engine, one must look to the southwestern edge of the Indian subcontinent, the geological cradle. The exacting atmospheric demands of piper nigrum dictate that it cannot thrive just anywhere on Earth. It requires a highly specific geological cradle.
This perfect, irreplaceable synthesis of deep geology, dramatic topography, and violent climate is found exclusively on the Malabar coast of southwestern India, a region nestled tightly against the foothills of the Western Ghats. The Western Ghats constitute a massive ancient mountain range, forming a sheer topographical wall that stretches for 1,600 kilometers along the western edge of the Indian peninsula. This towering, jagged barrier serves as the primary physical architect of the region's unique climate, manipulating the sky to feed the thirsty pepper vines growing in the jungles below. The massive spatial mechanics of the region's weather are driven entirely by the power of the Asian summer monsoon.
As the massive continental Asian landmass heats up under the intense summer sun, it creates a massive low-pressure zone that draws in heavily saturated humid air from over the Indian Ocean and the Arabian Sea. These low-level monsoon westerlies, bent by the Earth's rotation, carry unimaginable volumes of liquid water directly toward the Indian subcontinent at high speeds. Approximately 40 kilometers inland from the coastline, these moisture-laden winds collide violently with the steep, rocky western escarpments of the Western Ghats. Unable to pass horizontally through the solid stone of the mountains, the wet monsoon winds are forced aggressively upward into the cooler, thinner layers of the atmosphere.
This sudden, violent change in altitude and atmospheric pressure causes rapid cooling and condensation, resulting in explosive orographic precipitation. The skies literally open up, dumping between 2,000 and 4,000 millimeters of heavy rain annually onto the windward, western-facing slopes of the mountain range. This violent meteorological mechanism guarantees the exact 70 millimeters of early summer rain and the subsequent 16 weeks of continuous daily showers that piper nigrum absolutely requires to initiate its fruiting cycle. However, relentless pounding rain alone is not enough to sustain the delicate pepper vine. The earth itself must be capable of surviving the daily deluge without turning into a stagnant swamp. The soils of the Western Ghats are predominantly laterite soil, a unique geological cradle forged by millions of years of intense, repetitive tropical weathering. The constant, pounding monsoon rains perpetually wash over the ancient basaltic and granulite bedrock of the region, creating a severe chemical leaching effect deep within the earth. Over millennia, this moving water completely strips away the soluble silica and basic nutrient minerals, leaving behind a highly porous matrix dominated almost entirely by heavy iron and aluminum oxides. This exceptionally high concentration of oxidized iron is precisely what gives laterite soil its distinct rusted red coloration and its remarkable shape-shifting physical properties. When buried deep beneath the shaded jungle canopy and saturated with monsoon water, laterite is relatively soft, clay-like, and easily cut with simple hand tools. Yet, when it is exposed to the open air and dried by the intense tropical sun, it undergoes an irreversible chemical hardening process, baking into a material as dense and impenetrable as kiln-fired brick. This unique vesicular structure provides the laterite soils of the Malabar coast with exceptional porosity and incredibly rapid water drainage capabilities. For the wild Piper nigrum vine, this fast-draining lateritic terroir is quite literally a matter of life and death. The vine's shallow root systems require constant, high-level moisture to support rapid upward growth, but they are highly susceptible to devastating fungal diseases, such as Phytophthora root rot, if left submerged in standing water for even a few days. The laterite soil's unique physical ability to instantly drain the massive, overwhelming volumes of monsoon rainwater away from the root systems ensures that the vines receive the hydration they need without ever drowning. The water moves swiftly through the porous, rusted earth, leaving the roots damp, oxygenated, and perfectly healthy. Furthermore, the highly leached, acidic nature of this rusted soil, which typically sits at a remarkably low pH between 4.5 and 5.5, creates a harsh but optimal chemical environment that the wild pepper plant evolved to dominate. While other agricultural crops struggle to survive in such acidic, nutrient-depleted dirt, the black pepper vine thrives, utilizing its specialized root systems to extract whatever trace minerals remain in the iron-rich matrix. The soil's high sand fraction and low clay content further prevent compaction, allowing the vine's fragile feeder roots to expand rapidly in search of sustenance. This is the very essence of the Malabar terroir, a perfect, unyielding convergence of stone, wind, and water. The mountains force the sky to rain with violent intensity, and the leached, rusted earth quickly drains the water away before it can drown the jungle. Together, the towering peaks of the Western Ghats, the violent atmospheric mechanics of the monsoon winds, and the highly porous laterite soils created an irreplaceable, localized ecosystem. It was here, and originally only here, that the climbing botanical engine of Piper nigrum could reliably, continuously produce its immensely valuable fruit year after year, century after century. Harvesting and processing. The human element. While the rusted earth and the monsoon sky conspired naturally to grow the pepper, extracting it from the dense, tangled jungle canopy required immense human suffering, physical dexterity, and agricultural ingenuity. Harvesting Piper nigrum has historically been, and largely remains, one of the most physically demanding and dangerous agricultural practices in the world. Because the vines naturally climb high into the upper reaches of rough-barked host trees, the valuable, dangling, fruiting spikes are suspended far beyond normal human reach. To claim the lucrative harvest, ancient Dravidian farmers had to venture upward into the treacherous, rain-slicked heights of the jungle canopy, using nothing but crude tools and physical balance. The physical terrain of the Western Ghats is inherently hostile to organized agriculture, characterized by incredibly steep, muddy slopes and uneven, rocky ground that defies modern mechanization.
To access the high-hanging fruit, laborers traditionally utilized single-pole bamboo ladders, primitive and highly unstable tools specifically designed to be wedged against the vertical trunks of the towering support trees. Scaling these slender, flexing poles required exceptional physical skill and core strength, forcing workers to balance precariously 20 to 30 feet in the air while battling high coastal winds and severe muscle fatigue. The constant, oppressive humidity fostered slippery, moss-covered bark on the host trees, making every single ascent a potentially lethal undertaking. Furthermore, the traditional harvest occurs immediately following the cessation of the monsoon rains, a specific time of year when the dense jungle is exceptionally hostile and teeming with biological threats.
Laborers were forced to manually nip the tough stems of the spikes from the lateral branches by hand, a slow process that required them to linger in the canopy for extended periods. While balanced on their bamboo poles, these workers frequently endured relentless, painful ant bites, swarms of mosquitoes, and the terrifying presence of venomous snakes hiding perfectly camouflaged within the dense, wet foliage. A single misstep on the bumpy, steep terrain below, while maneuvering the heavy, cumbersome bamboo ladders, could easily result in catastrophic bodily injury or death. It was this immense physical difficulty, danger, and geographical isolation that actively helped cement the mythology of black pepper in the minds of early European and Arab traders. Because the merchants rarely saw the treacherous harvests themselves, they readily believed local legends that the spice was guarded by mythical serpents and dragons that had to be driven away with fire. This intentional mystification of the labor process only served to drive the price of the spice higher, transforming it into a luxury good that was frequently traded ounce for ounce with pure silver in the markets of Rome and Alexandria. Once the human element successfully extracted the green fruit from the dangerous canopy and returned it to the village floor, the complex, highly controlled art of botanical processing began.
The true economic genius of the pepper trade lies in the fact that the exact same harvested drupe can be transformed into 3 entirely different culinary products based solely on human manipulation of its biological decay.
Through carefully managed exposure to ambient heat, standing water, and direct sunlight, the ancient farmers learned to engineer distinct spices from a single, unified harvest: black, white, and green peppercorns.
Black peppercorns. To create the standard, globally recognized black pepper, the fruiting spikes are intentionally harvested prematurely, while the fleshy stone fruit is still hard and distinctly green. The individual drupes are manually separated from their stems and briefly blanched by being submerged in boiling water for approximately 10 minutes.
This sudden, violent thermal shock cleans the exterior of the fruit and purposefully ruptures the internal cellular walls, initiating a critical enzymatic fermentation process. The wet drupes are then spread out on woven palm leaf mats beneath the intense tropical sun for 5 to 12 days. As the fruit dries and dehydrates, the rapid oxidation of internal phenolic compounds causes the outer skin to shrivel, cement itself permanently to the inner seed, and turn a dark, highly wrinkled black. White peppercorns. Processing white pepper requires significantly more time, labor, and microbiological patience. The drupes destined for white pepper are left on the vine until they are fully mature, ripening to a bright, soft, yellowish red. After careful harvesting, these ripe, sugary fruits are packed into coarse sacks and submerged in slow-moving water or stagnant pools for 1 to 2 weeks, a traditional decomposition process known as retting. The prolonged aquatic submersion promotes a highly controlled bacterial fermentation, largely driven by naturally occurring bacillus species, that slowly rots and dissolves the fleshy outer pericarp of the fruit. Workers then aggressively rub the fermented, foul-smelling drupes by hand to strip away the decayed skin, revealing the smooth, pale, hard inner seed. This naked seed is thoroughly washed and sun-dried, yielding a significantly milder, earthier spice, completely devoid of the black pepper's sharp, fruit-driven external bite. Green peppercorns. To produce green pepper, the drupes are harvested at the exact same unripe, immature green stage as those destined to become black pepper. However, to forcefully halt the natural oxidative enzymatic reactions that would normally turn the fruit black upon exposure to air, the green drupes are immediately chemically preserved. Historically, this preservation was achieved by aggressively submerging the freshly picked fruit in strong, highly concentrated saltwater brines or acidic vinegars. Modern industrial methods now utilize advanced low-temperature freeze-drying or mechanical far-infrared dehydration, allowing the delicate peppercorn to retain its vibrant green color and its highly fresh, tart, and herbaceous flavor profile without the need for liquid brines. This profound mastery over the biological decay of the fruit allowed the merchants of the Malabar coast to carefully control the exact flavor profiles shipped westward across the Arabian Sea. Whether boiling, rotting, or brining the drupe, the farmers were fundamentally manipulating the active chemical compounds locked tightly inside the seed. And it was one specific, highly potent chemical compound, isolated deep within the pepper's core, that would ultimately conquer the sensory desires of the world: the chemical hook. The intense, enduring global addiction to black pepper cannot be explained by agricultural economics or unique spatial geography alone. It must be understood through the complex lens of human neurobiology. The allure of the spice lies entirely in a chemical illusion of fire, a botanical trick played directly on the mammalian nervous system. Hidden securely within the inner core of the pepper drupe is piperine, a potent hydrophobic alkaloid specifically engineered by the plant as a natural defense mechanism against hungry herbivores. For millions of years, the wild vine utilized this highly toxic chemical to actively deter insects, fungi, and grazing mammals from consuming and destroying its reproductive seeds. Yet in a twist of evolutionary irony, humanity turned this biological weapon into a driving culinary obsession. To truly understand how the piperine molecule works its magic, we must look at the microscopic molecular mechanics of the human sensory system.
Within the soft tissues of the mouth, tongue, and along the entire digestive tract, humans possess highly specialized sensory neurons equipped with transient receptor potential vanilloid 1 (TRPV1) channels. The TRPV1 receptor acts as an internal molecular thermometer, a complex ion channel explicitly designed by evolution to detect dangerous, noxious heat, specifically warning the brain of tissue-damaging temperatures above 43 degrees Celsius. When a person drinks scalding hot tea or eats burning food, the intense thermal energy triggers the TRPV1 receptors to wrench open, flooding the local nerve endings with calcium cations and firing a desperate high-speed pain signal directly to the brain.
Piperine is a master of chemical deception, possessing the unique ability to completely bypass thermal heat and trigger these receptors chemically. When a crushed black peppercorn touches the wet surface of the human tongue, the hydrophobic piperine molecules easily penetrate the cellular membranes of the oral sensory neurons. Though piperine completely lacks the specific vanillyl structural group found in capsaicin, the well-known compound that makes chili peppers hot, it still manages to forcefully and efficiently interact with the human TRPV1 receptor. Advanced computational structural modeling reveals that piperine bypasses the standard binding pockets used by other spicy molecules, instead interacting directly with the pore-forming S6 segment of the receptor, binding specifically at the amino acid residue T671. By physically binding to this critical inner pore, the piperine molecule acts as a powerful agonist, forcing the TRPV1 ion channel to wrench open at normal, safe room temperatures. The affected nerve endings immediately depolarize, and a massive, unregulated influx of calcium cations rushes violently into the cell. The human brain receives this sudden, violent electrical signal and interprets it exactly as the receptor biology intends. It registers the acute sensation of literal burning heat. There is absolutely no actual physical temperature increase in the mouth, nor is there any real thermal tissue damage occurring to the cells. But the chemical illusion of fire is absolute and undeniable. Interestingly, detailed electrophysiological patch clamp studies have demonstrated that while piperine is technically a less potent molecule than capsaicin, it exhibits a remarkably higher efficacy at keeping the human TRPV1 channel locked in an open state. Furthermore, piperine induces a profound rapid state of receptor desensitization and tachyphylaxis within the nervous system. After the initial violent shock of the peppery bite, the repeated application of piperine forces the local pain receptors to rapidly exhaust their signaling capabilities, significantly diminishing the electrical current and leaving behind a lingering, pleasantly warm numbness in the mouth. This specific neurobiological sequence, a sharp, alarming burst of illusory pain followed rapidly by a soothing, warm numbness, is the physiological foundation of humanity's profound addiction to the spice. From a strict evolutionary biology perspective, humans should inherently and universally reject ipopenine. Mammalian survival instincts are hardwired to associate bitter, sharp, or painful tastes with poisonous environmental alkaloids or dangerously rotting food. The human body initially treats the piperine molecule as a literal, life-threatening attack on its survival, activating sympathetic autonomic stress responses, increasing the heart rate, and sometimes even inducing physical sweating or mild mucosal blistering. Yet humans consistently and deliberately seek it out, putting it on nearly every dinner table in the modern world. Psychologists term this unique behavioral phenomenon benign masochism. When the mouth violently signals that it is burning, the brain immediately triggers a localized panic response, releasing a heavy flood of endogenous opiates, or endorphins, to naturally kill the perceived pain and soothe the body. However, the higher cognitive functions of the human frontal cortex quickly realize that the body is not actually in any real danger. There is no physical fire, the food is safe, and the threat is entirely an illusion.
The illusory pain rapidly vanishes due to tachyphylaxis, but the chemical endorphin rush remains in the bloodstream, resulting in a sudden, lingering sense of euphoria and pleasure. This opponent process theory of acquired motivation perfectly explains why black pepper transcends the status of a mere flavor enhancer. The spice literally chemically hacks the human nervous system, turning a highly evolved defensive botanical toxin into a remarkably reliable trigger for human pleasure. By repeatedly exposing themselves to the controlled, ultimately harmless pain of the piperine molecule, ancient humans essentially learned to harvest a mild endorphin rush on demand, entirely separated from actual physical harm. Thus, the aggressive jungle vine that changed the world did not do so merely by tasting pleasant. Piper nigrum conquered the globe because it was the perfect biological machine, thriving strictly in the treacherous, rain-soaked geological cradle of the Western Ghats, and yielding a fleshy stone fruit armed with a highly specific molecular key. When the ancient, daring farmers of the Malabar coast braved the sheer, slippery heights of the monsoon-drenched canopy to harvest this tiny seed, they unlocked a chemical illusion that would permanently rewire the human palate. The relentless desire for that fleeting, fiery rush of piperine would soon launch 1,000 European ships, violently redraw the maps of continents, and usher in the turbulent dawn of a truly globalized world.